Summer, 1944. At Aberdeen Proving Ground, engineers watched the range shake under shell fire. A Sherman tank stood motionless in the haze, armor pocked by 30 black circles where shells had struck. Each detonation rang through the field, each echo proving the same cold fact: the welds still held. The seams looked crude, uneven, almost careless, yet they refused to tear. Under magnification, the joints showed no cracks, only compressed ripples of metal that had somehow outlasted physics. The name on the test log was unfamiliar: a welder from Detroit Tank Arsenal disciplined weeks earlier for violating the manual. His offense was simple: he welded upside down. Every textbook called it impossible. Every foreman laughed. But the hull before them told a different story. The supervising engineer lowered his clipboard. "Run another 10, he said. The gunnery crew reloaded. Shells struck, dust rose, and the tank did not fail. By dusk, the firing line fell silent, smoke drifting over steel that refused to break. The last report of the day carried one question written in pencil: how did a forbidden weld survive 30 direct hits? No one could answer yet, but the war's next revolution in armor had already begun, with one man turning gravity against itself. By 1943, the U.S. Army Ordnance Department faced a quiet crisis. Sherman tanks that should have endured single hits were failing at their seams. Weld lines once thought indestructible were opening under shock. Metallurgists traced the cause not to the steel, but to how it was joined. Across factories in Michigan and Ohio, welders followed the manuals without question: flat, fast, and efficient. Those very manuals forbade one position above all others: overhead. The note was absolute: never weld upside down. At the Detroit Tank Arsenal, a man named Morris Parker ignored that line. He had come from the shipyards where hulls were stitched in every angle the sea demanded. Late one shift, frustrated by weak penetration along a side plate, he rolled the piece and struck an arc from below. Sparks rained across his visor. The foreman shouted, certain the bead would fall apart. But when the hammer test came the next morning, the tone was solid. Curious, the inspectors sent the sample for X-ray. The image surprised them. The inverted seam showed no voids, no trapped slag, just a tight fusion zone, denser than anything from the horizontal line. Parker claimed the molten pool behaved better upside down, compressing into itself instead of spreading flat. The engineers dismissed it as chance and tagged the piece for scrap. Weeks later, Shermans returning from North Africa told a different story. Cracks appeared along perfect horizontal seams, while a few hulls patched with Parker's method remained intact. The anomaly reached a junior ordnance officer who ordered controlled tests. In February 1944, at Depot No. 3 near Chester, 12 armor plates were welded, half by standard procedure, half inverted. When struck by armor-piercing rounds, the conventional joints fractured after 10 impacts. The inverted plates absorbed all 10 without separation. The data was clear, but the rulebook was stronger. The supervisor marked the report inconclusive and forwarded it to Aberdeen. Rumors spread through the repair lines before the ink dried. Welders whispered about the upside-down fix. Some laughed. Others began to try it after hours, when inspectors had gone. Under flickering lamps, sparks rose from beneath the steel, lighting the shop floor in strange reflection. No one yet knew that one man's defiance of gravity had just altered the geometry of survival, and that the next test would make his forbidden weld impossible to ignore. By March 1944, the Ordnance Department moved from rumor to protocol. Parker was called from Detroit to a cold evaluation hall near Cleveland, a space built to remove luck from the equation. Armor plates lined the walls like dull mirrors. A test crew in gray coats checked meters and notebooks. Captain Ross greeted him with formality and a single sentence. He said the arc would decide, not opinion. 2 identical plates of rolled homogeneous armor were set on adjustable frames. One plate faced the welder for a standard horizontal pass. The second plate was rotated until its seam sat overhead. Technicians mounted thermocouples along both pieces, clipped strain gauges near the joint toes, and calibrated a chronograph that ticked once each second. Data would speak in numbers only. Parker worked first on the conventional plate. He held a steady arc, advanced at an even pace, and left a wide, familiar bead. The pool spread and cooled with visible ripple marks. He shifted to the inverted plate and changed nothing but posture. The arc shortened by instinct. The molten pool gathered tight against gravity, a compact oval that rolled forward in small pulses instead of sagging. Meters told the story the eye could not. Heat traced across the inverted seam more evenly. Cooling contraction measured lower by the strain gauges. Under the lens of a portable microscope, the fusion zone looked denser and deeper. Parker made no speech about it. He only said the puddle felt self-contained and that the sound of the arc told him when to move. After cutting the samples, the team polished cross-sections and recorded the microstructure. The standard seam showed tiny voids along the center line. The inverted seam showed clean fusion and a narrow heat-affected zone. Tensile pulls taken on a screw press yielded a pattern the lab could not ignore. Average strength rose by 18% on inverted runs. Replication was the next hurdle. 5 welders attempted the method under the same settings. 4 produced unstable pools and scattered slag. 1 came close to Parker's control, but his bead wandered. The inconsistency gave skeptics an obvious argument. They said the method worked only in the hands that invented it. Captain Ross agreed to a second round, this time with controlled parameters. McCrae entered the process with a scientist's caution. He defined a narrow window for success. Preheat would be 150 degrees Celsius. Current would range between 200 and 220 amperes. Travel speed would stay near 2 millimeters per second. Bead width would target 6½ millimeters. Interpass cooling would last 2 minutes. Arc length would shorten by a few millimeters. With those limits, replication improved. 3 welders produced stable inverted seams that passed quick X-ray checks on site. Slag separated cleanly. Porosity markers fell to near zero. The lab crew repeated tensile pulls and bend tests until the numbers settled. The advantage held. The method no longer looked like a trick. It looked like a process waiting for proof under fire. Aberdeen ordered full sections. 6 hull joints were fabricated from armor stock and delivered to the range. 3 were welded by the book. 3 followed the inverted sequence under Parker's guidance. Each section weighed several tons and carried witness marks for high-speed cameras. The firing plan called for armor-piercing rounds at 300 yards, stepped in 5 shot series. The first series hit a standard seam. A fine crack flashed along the bead line after the 3rd impact and propagated under the 5th. The joint opened. The second series struck an inverted seam. The plate dented and bowed, but the weld line held. Strain gauges recorded spikes, decay, and returned to baseline. The camera showed a ripple traveling across the fusion zone like a wave. The trial continued until the ammunition allotment ended. Standard joints failed early and visibly. Inverted joints absorbed the sequence with deformation rather than rupture. Aberdeen wrote a dry summary that avoided adjectives. It listed amperage, travel rates, preheat, bead dimensions, and impact angles. It closed with one finding. Under defined settings, inverted manual arc welding maintained integrity under repeated ballistic shock. Washington reacted with caution. A telegram instructed Detroit to suspend non-standard welding until reproducibility reached industrial scale. Parker returned to find his bay closed and a notice about safety on the door. On the floor at night, the notice changed nothing. Crews practiced on scrap and traded notes in pencil. They learned to hear the low hiss that meant stability and to stop when the arc turned harsh. McCrae refused to let the paper trail end. He wrote a short syllabus that fit in a tool roll. It taught the inverted posture with a 5-degree rise, short arc discipline, and 2-inch beads broken by brushing. It warned about arc blow and contamination. It described how to angle the rod to push slag forward and away. Copies spread faster than permission. A second laboratory cycle tightened the chain of cause and effect. Metallographers etched samples to reveal grain flow. Inverted beads showed compression oriented across the joint. Residual stress mapped lower at the toes. Fatigue rigs cycled test coupons through vibration until failure. The inverted samples lasted longer under the same load, not by a small margin, but by a margin that changed maintenance math. Film provided the most persuasive evidence. A Bell and Howell camera captured overhead passes at high speed. The frame showed the molten pool curling inward and setting under a skin. It did not drip. It did not wander. It advanced in measured pulses that left a narrow and even ridge. Engineers who distrusted stories trusted the frames. The arc geometry could be seen, not argued. By early May, the report was revised with conservative language and hard numbers. It avoided names and kept to repeatable steps. It recommended use on armor thicker than 50 millimeters, where standard passes showed distortion and early cracking. It called for a magnetic particle inspection on every seam and random ultrasonic checks. It asked for rotators to reduce posture risk and increase repeatability. The answer from the War Department was a partial no, dressed as delay. Training costs were too high in the middle of a campaign. The manual would not change mid-year. Yet the data did not vanish. It moved sideways through the Ordnance network and reached the shops that could not wait. Frontline depots adopted the steps without ceremony and welded the way survival demanded. In those bays, the method shed theory and grew practical edges. Crews learned to mark bead length in chalk and to count seconds allowed to hold the cooling rhythm. They set preheat with stove thermometers and watched color rather than rely on guesswork. They logged amperage in grease pencil on the plate itself. Numbers pinned habit to metal until the sequence felt ordinary. The final detail that convinced the last skeptic was small. On cut sections of inverted seams, the heat-affected zone measured narrower by a few millimeters. That meant less brittle land on either side of the joint. Under impact, the transition held like a muscle crossing a joint, not a hard plug trapped in rigid bone. When that phrase entered a lab notebook, the argument ended. By the time the Cleveland Hall shut down its test rigs, the design of victory was no longer a design, it was a discipline. The method lived in amperage tables, in bead lengths, in rest intervals, and in inspection routines. It lived in the steady sound welders learned to hear when the pool was right, and it waited for Aberdeen to write one more line that would move it from rumor to rule. June 1944. Rumor moved faster than orders. Across the repair depots of southern England, welders began to rotate plates, crawl beneath hulls, and strike arcs where the manual said never. They called it the inverted pass. There were no classes, only sketches on greasy paper and pencil arrows marking angle, travel, and rest. Night shifts made it easier. With officers asleep, chains lifted side plates and torches stitched narrow ridges against gravity. The seams looked plain. The results did not. Tanks patched that way took punishment and stayed in the fight. The first large trial came by logistics rather than design. A queue of Sherman hulls from gunnery workups reached the Portsmouth depot with a shortage of proper fixtures. To keep tempo, a foreman ordered turret rings hung upside down and sponson plates set on improvised jigs. Several welders used the posture they had heard about, cleaned between short beads, and left the distinctive dark ridges. A lieutenant filed a routine note about unusual bead texture. 2 weeks later, those hulls went to a training range on Salisbury Plain. After more than 200 impacts across the group, none of the inverted seams separated. Detroit heard the echo as numbers, not stories. The Arsenal compiled a mid-month chart of structural failures and found a sudden drop in returns from one line. Records showed that line worked nights with an old team from Parker's Bay. Scrap fell by tons. Rework hours eased. The superintendent did not issue praise or punishment. He circled the plot with a pencil and wrote one word in the margin: hold. He wanted to see if a second month would repeat the pattern. It did. There was still no sanctioned method, only emergent habit. Engineers argued about why the seams endured. Some said the weld pooled tighter and cooled under compression. Others said chance and selection bias. In the bays, men stopped arguing and watched the puddle. They listened for a low hiss that meant stability. They cut their beads short, brushed hot, and advanced in small pulses. The torch taught them more than memos could. At Aberdeen, Captain Ross began to see the change in shipping crates. Tanks arrived from English depots with narrow-ridged seams that did not match the handbook. On his range, those seams outlasted the standard pattern under controlled fire. 15 hits passed, 20 hits passed, sometimes more. He pulled the logs and read entries from field repair crews. The same phrase recurred in careful handwriting. Upturned fixture, overhead sequence. He did not yet have a theory. He had a correlation he could not ignore. McCrae traveled from Cleveland with a box of films and a notebook of measured settings. He avoided grand claims. He carried temperatures, amperage ranges, bead widths, and rest intervals that field welders could keep in their heads. He argued for clarity over charisma. Define what to do, then measure what it does. Ross agreed to a discreet study that would not appear on public schedules. The program took a spare room and a working name that said only what it was: Project Invert. The first Aberdeen cycle stayed modest. Crews built instrumented coupons, welded both ways, and fired in the same sequence. Metal told one story again. Standard joints cracked early and clean. Inverted joints bowed and lived. Cameras recorded at a few hundred frames each second. When played back, the fusion zone of the inverted seam showed a small wave ripple, a visible sign that shock was traveling and thinning rather than stopping and breaking. A metallurgist in the room called it a hinge. He meant it as a metaphor. The image stuck. Field adoption did not wait for a conclusion. In hedgerow country, units patched with whatever posture held. Reports from the breakout named Operation Cobra arrived with dry language and hard detail. Several Shermans listed more than 20 confirmed hits and returned under power. Inspection notes described dark, narrow seams that resisted separation even when the surrounding plate was dented beyond recognition. Crews gave the lines a nickname that moved from mouth to mouth: ghost welds. They looked ordinary and behaved otherwise. Detroit scaled what it could without changing titles. A maintenance team built crude rotators from aircraft bearings and salvaged motors. The rigs turned entire hulls a quarter turn at a time. A welder could stand upright while the steel rotated into the inverted position around him. The puddle behaved the same. The posture risk fell. Management accepted the rigs as fixtures rather than doctrine. Throughput rose. Noise fell as long drag beads gave way to short-counted pulses. Numbers hardened the trend. Weld rejection dropped from 1 in 12 to 1 in 40. Turnaround per hull slid from 40 hours toward the upper 20s. Backlog charts bent downward for the first time in years. The floor quieted into a pattern supervisors began to call by a plain phrase: quiet steelwork. Every inch was counted. Every minute had a reason. In England, a senior depot officer asked for a simple statement he could post above the bays. McCrae wrote a line in pencil and handed it over: short arc, short bead, clean hot, keep the rise. It was not a theory. It was a sequence a tired man could follow after midnight. Copies spread without letterhead or signature. They were folded into pockets and taped to lockers where gloves and brushes hung. Washington hesitated on principle. A draft memo asked whether a mid-campaign posture change would raise injury risk and slow output. Another asked who would be responsible if an inverted seam failed in combat. Aberdeen answered in the same cold language it used for ballistics. The method reduced cracks under impact and vibration by measurable margins. It required inspection changes and fixtures for repeatability. It did not make speed the target. It made integrity the target. The debate moved upward and sideways at once. Ross prepared one more range plan before the snow. He ordered thicker coupons and heavier instrumentation. He wanted strain maps, not only film. He wanted to see where the metal carried pain. As he reviewed the schedule, he realized the study had crossed a line. It was no longer about one welder who broke a rule. It was about a repeatable geometry of survival. The range crews chalked circles on armor plates, checked lenses, and logged temperatures as a cold wind crossed the field. By early autumn, Project Invert had stopped being a rumor, a trick, or a grievance. It was an arc discipline, a rest rhythm, and a pattern of inspection that crews could enact under pressure. It had moved from a night habit to a day routine without a change in the book. The book would catch up later. For the moment, Aberdeen prepared to document a demonstration in full view, with witnesses who doubted and with gauges that did not. What followed would decide whether the method stayed a fieldcraft or became a standard line in the language of war. By autumn, secrecy gave way to structure. McCrae's team condensed every observation into a 2-page field syllabus designed to survive mud, oil, and fatigue. It listed amperage from 200 to 220, bead length of 2 inches, brush between passes, and a 5-degree upward tilt to feed slag out of the pool. Beside each line stood a cause and effect. Long bead equals trapped gas, cold plate equals brittle root. Welders carried the sheet folded inside tool rolls. It was not a command, it was proof that someone had already measured what worked. Inspection routines changed next. Flat seams once relied on hammer strikes and random X-rays. The inverted sequence demanded new habits: magnetic particle checks after each shift, ultrasonic scans every 10th seam, and a recorded cooling interval for traceability. At first, men complained that the paperwork slowed them. A month later, when rejection rates dropped and scrap piles shrank, no one wanted the old way back. Depot workshops began building their own rigs from scrap beams and chain hoists. One man could now rotate a hull 90 degrees, lock it, and stand beneath a side plate without crouching. It looked crude, but within a week the bays ran smoother. Crews learned to read the arc by sound alone. A steady hiss meant penetration. A coarse buzz meant contamination. Inverted welding had its language, taught not by officers, but by rhythm. Field trials expanded across Brittany. A liaison team from Aberdeen conducted live tests on 12 tanks, half standard, half inverted. The result repeated itself with mathematical patience. Traditional seams cracked after 10 rounds. Inverted seams showed none. Temperature, angle, and voltage all aligned to one pattern: tension absorbed, not resisted. The finding was written into a report with no adjectives and sent directly to Washington. At Aberdeen, the final demonstration took shape. A full Sherman hull, welded entirely by the inverted process, stood on a concrete pad. Cameras waited, gauges wired to the seams. 30 armor-piercing shells were loaded in sequence. The range fell silent except for the wind. The first 5 rounds struck low, denting but not tearing. 10 rounds in, the chalk markings disappeared. 20 in, the gauge needles flicked and returned to 0. At 30, the order came to cease fire. Smoke lifted. Inspectors walked forward with mirrors and die kits. Not a drop of red bled from the weld line. The joint, narrow and dark, remained intact. Micro-strain records later showed that what eyes had missed. Each impact spread energy along the seam like ripples, then settled without fracture. Aberdeen wrote the finding in the same neutral tone it used for every weapon test. Integrity maintained after 30 direct impacts. No visible or subsurface crack detected. Ross filed the range report himself. He struck adjectives, shortened phrases, and listed only verifiable data: current, temperature, arc angle, preheat, shot count. The closing line read, "Recommend field adoption with controlled fixtures and certified inspection." McCrae added a short annex on safety: visor shrouds, backhand technique, and timed pauses to cut fume exposure. Injury rates dropped once welders stopped forcing long beads and treated each pass as a separate stroke. Production centers acted before approval arrived. Detroit integrated motorized rotators that turned full hulls in 4 increments. Welders could remain upright while the armor revolved, producing identical inverted geometry without physical strain. It kept the method within rulebooks while preserving the same stress pattern in metal. The compromise turned defiance into process. Throughput rose again. Field dispatches became the silent evidence. A report from the 7th Armored Division noted a tank hit 17 times along one seam that still drove 50 miles back to refit. Another from the Guards Armored described a recovery crew replacing a failed flat joint with an inverted one. The tank re-entered combat within a day. None of these entries used names. Each ended with the same mechanical phrase, "No breach observed." By October, Aberdeen's strain charts, depot statistics, and field logs all converged. The inverted seam behaved like a flexible joint rather than a brittle bond. The method's risk was human, not mechanical. With rotators in training, even that faded. What remained was a reproducible sequence: heat, short arc, pause, clean, repeat. Approval came quietly. A War Department memorandum, signed in pencil and dated November 12, 1944, authorized limited field rollout of inverted manual arc procedure for RHA armor repair. It required inspection logs and adherence to McRae's parameters. No one mentioned Parker by name. By year's end, the shift was complete. Across depots from Antwerp to Nancy, the bays glowed deep orange through the night. Welders counted seconds between pulses, brushed the slag before it cooled, and checked color for temperature instead of guessing. Tanks rolled out with seams so uniform they no longer drew questions. The method had crossed from rebellion to routine. One hull from the Aberdeen trial was kept at the range. Visitors would later run a hand along the dark ridge where 30 shells had struck and failed. The surface felt rough but unbroken, a quiet monument without a nameplate. It did not commemorate invention or defiance. It stood for a moment when metal, fire, and persistence had agreed on a single truth, that strength was not found in resisting force, but in yielding just enough to survive it. Winter 1944 froze Europe in steel and silence. Tanks crawled through snowbound forests, where seams, once feared for weakness, now carried the full weight of battle. In the repair depots of Belgium, welders worked in air so cold their breath fogged inside their visors. Sparks hissed against frost and clung to armor like fireflies. And through that bitter winter, a small miracle repeated itself without ceremony. Seams welded by the inverted sequence refused to fail. Aberdeen's December audit recorded it first. Crack rates on armor joints had fallen from 32% to less than 4%. Analysts traced every surviving plate to the same set of repair logs marked overhead procedure. The numbers left no room for debate. For every 100 tanks struck, nearly 20 crews survived because their hulls stayed sealed long enough to escape. The report reached Washington in plain type with one note scrawled in pencil: "Gravity has been defeated." Detroit Arsenal translated the data into throughput. Repair time per hull dropped to 28 hours, and output peaked at over 300 a week. The new rotators turned a 35-ton hull in minutes. Welding halls that once roared with noise had fallen into a rhythm the foreman called quiet steelwork. Beads ran short and clean, inspections came faster, and the smell of ozone replaced the old stench of burnt slag. Production had learned patience. Parker remained in his corner bay, uncredited and unspoken of. His name appeared nowhere in reports, but the camera crews that filmed instruction reels used his hands. The reels ran 3 minutes, silent, showing only arc motion and brush angle. They circulated across depots under the title Welding Sequence, Controlled Inversion. Parker never asked for acknowledgement. When McRae thanked him, he only said, "It works, that's enough." January brought the final experiment Aberdeen had planned since summer: cold weather validation. Engineers welded test coupons at 15 below 0 Celsius and chilled them in open air before firing. Standard seams cracked on the second impact. Inverted seams bent, froze, and rebounded. Microscopes showed compression bands closing over microfractures like healed skin. One observer wrote, "The joint behaves as if alive." That sentence never appeared in the final report, but the data did. Residual stress reduced by 2/3, fatigue life extended by 40%. McRae compiled the year's results into a single technical brief, 40 pages of tables and photomicrographs. The conclusion was mathematical, not poetic. Inverted welding extended armor life by 300 operating hours and reduced maintenance downtime by half. Every parameter, amperage, bead length, cooling interval, formed a pattern of predictability. The weld had become a machine within a machine, a living hinge built from molten geometry. Still, bureaucracy needed its ritual. In February 1945, a technical committee gathered in Washington to debate the findings. Half the officers present had never seen a weld in person. The arguments circled doctrine and discipline. One colonel called the posture a breach of industrial order. Another replied, "So was radar." When the vote closed, the verdict passed by a single margin. Approved for field use where verified results exist. McRae left the room with no celebration. The sentence was short, but it opened a door wide enough for history to walk through. Orders moved fast once written. Depot commanders received a single encrypted telegram. Continue inverted sequence pending final manual revision. No signature, no context, but every man who read it knew what it meant. By spring, 70% of all U.S. armored repairs in Europe followed Parker's pattern. Instructors stopped calling it upside down and began calling it stable sequence welding. The slang disappeared, the science remained. Field logs told the story in human scale. In March, near Cologne, a tank was struck 17 times along a side plate. The driver later wrote that the floor flexed like a drum skin and then settled. When the crew dismounted, they found a deep crater along the seam, but no rupture. The report listed the hull as operational. The final line said only, "Still rolling." Another field unit documented comparative survival. Out of 100 tanks hit by anti-tank fire, 17 were recovered intact. 12 of those carried the new weld signature. The statistics were clear enough that command began adjusting supply forecasts. For the first time, mechanical durability outpaced combat attrition. The battlefield was consuming less steel than industry could now restore. In Detroit, the manual team drafted a revision to TM 92852. The proposed clause read, "Overhead welding permissible when penetration continuity and stress distribution meet or exceed horizontal standards." It was a single line, born from 2 years of defiance. Parker was invited to sit in on the review as a technical consultant. He arrived in his soot-streaked jacket and said little. When the committee chair asked if he recognized the clause, he replied, "That's the weld." In March, Aberdeen hosted one last observation firing before the process became law. 30 more rounds struck the same test hull used the year before. The old seams, now weathered and dark, held through every hit. Strain gauges flatlined at 0 residual stress. The welds had reached their limit and decided not to break. Ross watched in silence, then wrote in his logbook, "No further testing required." When the war's end arrived weeks later, factories slowed but did not stop. Welding halls stayed lit to process returning armor and refit vehicles for training. The method spread beyond tanks into shipyards, bridge works, even refineries. Engineers borrowed its math, not its legend. Manuals cited field observations, 1944, 45 with no names attached, but welders knew. They repeated Parker's rule in every shop from Michigan to Marseille. Short arc, short bead, clean hot. McRae retired from service the next year. His final memo, written in blue ink and folded into the project file, read, "Innovation often begins as an error that survives the test." He included a photograph of the Aberdeen hull with its 30 impact rings and sent a copy to Parker without signature. Parker kept it folded in his toolbox until he died. By the summer of 1945, American tank recovery rates had doubled. More than 800 crews credited the welds for their survival, though few knew why their seams had held. The factories never published a statement, and no citation mentioned an upside-down discovery. But inside every tank that crossed Europe's last battlefields, the proof remained. A dark line of steel drawn against gravity, joining plate to plate, unbroken beneath fire. When historians later reviewed the production data, they found the correlation that words could not flatten. The moment the inverted sequence reached mass use, tank loss curves bent downward for the first time. Attrition met resistance not from armor thickness or gun caliber, but from the invisible geometry of molten steel that chose to yield instead of shatter. It was the quietest victory of the war, and the one that kept the others moving. By autumn, the manuals went to print. The new paragraph stood among tables of amperage and bead width, a single understated instruction that summarized a revolution. Overhead position welding authorized where mechanical integrity exceeds standard. Beneath that dry sentence lived the war's simplest triumph, a weld that broke no rule except the one that said it could not exist. No medals were awarded, no ceremony marked the change, only the tanks themselves bore witness. Their scars formed a pattern engineers still trace in museums today, dark, narrow seams that caught light differently than the rest of the armor. Each one was a fingerprint left by hands that turned the world upside down to make it hold. When the furnaces went cold in late 1945, the war left behind more than wreckage. Inside the silent welding bays, the marks of the inverted seams still glimmered beneath a film of soot. Detroit Tank Arsenal mothballed its rotators, stacked unused electrodes, and swept the slag into gray piles. Yet the blueprints of Project Invert had already slipped into civilian hands. Copies of Aberdeen's final report found their way to shipyards, refinery contractors, and bridge engineers. The discovery was no longer military. It was mechanical truth. In Seattle, the Navy tested the method on destroyer hull plates. The same narrow ridges appeared beneath decks, and the same results followed. No cracks, no inclusions, full fusion. By spring 1946, the inverted weld was referenced in the ASTM provisional standards for structural joints. McRae's name appeared once, buried in an appendix. Observations derived from Armored Vehicle Research, 1944-45. He returned quietly to civilian metallurgy and never spoke of it again. Parker faded faster. His personnel file closed in 1946, listing him simply as welder, first class. Colleagues said he preferred the night shift, working under a single hanging bulb. When asked why he never claimed credit, he answered, "You don't own gravity." The phrase became a kind of code among those who remembered, the acknowledgement that his defiance had turned into doctrine. Aberdeen kept one test hull for study. Technicians uncovered it years later. 30 impact rings still visible, seam intact. Attempts to cut samples dulled the blades. They left it untouched, tagging it Specimen 30H. No memorial, no story, just a slab of steel that refused to fail. By 1950, as tanks rolled again in Korea, instructors taught the controlled inverted arc to new welders. The syllabus was stripped of names but not detail. Short arc, 2-inch bead, hot clean. Each phrase had once come from Parker's routine in Detroit. Every new apprentice learned it as law, never knowing its origin had been a forbidden act in 1944. In the decades that followed, the principle spread like a hidden current through engineering. Offshore rigs used it in storm assembly. Pipeline welders used it under river crossings. Studies on fracture mechanics confirmed what Parker had felt by instinct, that the inverted bead lived in compression, distributing force instead of locking it. The method turned resistance into resilience. By the 1960s, its geometry was drawn in textbooks as inverted stress equilibrium, explained in graphs but not in names. Parker's weld outlived its creator. When aging Shermans were cut open during range decommissioning, metallurgists found those same seamless grains beneath paint and rust. The weld lines were blackened but whole. The inspection notes, written 20 years after the war, repeated Aberdeen's phrase word for word, "No crack observed." Time stripped the context, but not the substance. Each bridge joint, ship keel, and refinery tank built after owed a fraction of its strength to the man who ignored a rule. The upside-down weld had become invisible infrastructure, a silent inheritance that kept holding under storms, heat, and stress. History seldom records hands, only outcomes. Yet in every beam or hull bearing that faint 5-degree rise, the trace remains. A human decision preserved in metal. The weld that defied command became part of command itself. And the man who turned the torch against gravity left a legacy measured not by his name, but by the unbroken seams still carrying weight long after his fire went out. In laboratories and museums, when engineers study specimen 30H beneath cool fluorescent light, they note the smoothness of its ridge and the perfect silence of its line. They write new reports about fatigue, resilience, and ductility. But the steel does not care for words. It answers only with the same unspoken proof it gave in 1944, that strength once discovered never needs permission to endure. The factory stands silent now. Dust coats the jigs and rotators that once turned armor like a clockwork of fire and noise. The walls still carry faint burn marks where arcs once traced light through smoke. Nothing moves, yet the seams remain. Narrow, dark, and unbroken, the same lines that once held against 30 direct hits. To most, they look ordinary. To those who know, they mark the place where defiance became law. At Aberdeen, the test hull endures beneath a canvas sheet. Rain beads along the weld and runs clean at its edge, unable to find a flaw. It has outlasted the range that built it, the war that required it, and the men who believed it would fail. The manuals call it inverted welding. The welders never called it anything. They simply trusted what worked. The rule they broke became the rule that stayed. Somewhere in the dim stillness of those bays, the echo of a single torch still lingers, the sound of steel cooling into discipline. It was the hum of gravity reversed, of metal persuaded to hold, and of a man who proved that strength is not loud. It endures quietly, exactly as he did.